Hi everyone, this is Prof. K again, and we're going to be talking about classifying chemical reactions, and specifically we'll be talking about reduction and oxidation reactions. And so this is chapter 7.2, part 3. So our learning goals for today are to define the 3 common types of chemical reactions, and we're going to finish that set with oxidation and reduction reactions because we've already talked about precipitation reactions and acid-base reactions. And along the way, if we identify something as a redox reaction, we're also going to compute the oxidation state for the elements in those compounds. And so to start, I want to define oxidation and reduction, or talk about how it's often referred to. So oxidation is often defined as the loss of electrons, while reduction is defined as the gain of electrons. And one way that I found helpful to remember this is Leo the lion says Gur. So Leo stands for lose electrons, it's oxidation. And Gur, said with a bit of an accent, stands for gains electron is reduction. And so you can potentially use this to help you remember what oxidation is versus reduction reactions. What do these redox reactions look like? And so in redox reactions, one or more atoms, or potentially a compound even, gains or loses an electron. And an example of this sort of reaction is if you add solid iron to with oxygen gas, you can get iron oxides. And so you can potentially rust your iron here. And so if we look at the half reactions for each of these atoms, so if I look at iron, at the start of this reaction, our iron doesn't have any charge. And at the end of our reaction, it's bound to oxygen, and all of a sudden it has a charge of 3+. So in order to balance this equation, we need 12 electrons to cancel out the positive charge here, which I then reduced just by dividing by 3, so we could potentially see it in a simplified form. On the other hand, oxygen also starts as a neutral compound with no charge, but has to gain electrons or have electrons added to it in order to have a balanced equation with the negative oxygen that's being produced in iron oxide. And again, I divide this reaction by 3 in order to look at it a little simplified. So if we look at this example, I want you to consider for these half reactions, which compound is oxidized in this reaction and which is reduced. So you can pause the video and think for a second, and then I'll talk about how we can tell. So if we look at the iron half reaction, what we have is that iron is releasing electrons into our system, which means that iron is losing electrons, and Leo the lion. So Leo, this is being oxidized. On the other hand, O2 is gaining electrons, so it's being reduced. So this is how we can potentially identify something as having been oxidized or been reduced using these half reactions, or losing what we know about whether it gains charge or loses charge. And so if something starts out as neutral and becomes positive, it's been oxidized. If something starts out as neutral and becomes negative, it's been reduced. So this is some of the language that we'll practice using. Additionally, we also have specific vocab we use called a reducing agent and an oxidizing agent. And so a reducing agent is the species that gets oxidized and therefore has performed some reduction as the agent of that action. So here, our iron was oxidized, which meant that it reduced our oxygen. And on the other hand, our oxygen is the species that reduced, which means it's acting as the oxidizing agent for oxidizing iron. And so the language refers to how it's acting. So if it is a reducing agent, then it's losing its electrons in order to perform that reduction. So we just need to kind of practice using this language and try to get used to talking about something being reduced versus performing a reduction or being a reducing agent. And so we'll have more practice with this, but I wanted to point out the specific vocab and give you some definitions so that you can better approach these problems. And so I also mentioned that we're going to talk about oxidation state. And so when you have a loss of electrons, it leads to an increase in this oxidation number, which I'm about to define. Whereas with reduction, you have a decrease in oxidation number. And so this is another common definition you might see for oxidation and reduction, and it relies on you being able to define oxidation number. So oxidation number is the charge an atom in a compound would possess if that compound were ionic. And it's also known as oxidation state. So we can say oxidation state or oxidation number interchangeably, and we will do so in this course. So if we think about an ionic compound, such as potassium chloride, we can imagine that this potassium would be K1 plus, and chlorine would have a charge of 1 minus. And what that manifests as is a oxidation number or oxidation state of potassium being +1 and a chlorine oxidation state being -1. And you'll notice that I flipped the order of the number and the sign because for oxidation state, we do put the plus sign or the minus sign first and the number, and it helps us distinguish between when we're specifying charge and when we're specifying oxidation state. So I just want you to notice that I made this change. Now, HCl is something that we would identify potentially as a polar covalent bond with the material we've already covered in this course. But if we pretend it's ionic, then we will once again have Cl1 minus, and in order to balance this reaction, we have H1 plus, which means that the oxidation state for hydrogen is going to be +1, and the oxidation state for chlorine is going to be -1. And so these last two examples, I haven't shown you how you might calculate it yet, but we can potentially try just to guess based on what we know about the periodic table. So oxygen typically has an ionic charge on the periodic table of 2 minus, which means its oxidation state is -2. Hydrogen, on the other hand, tends to like to hang out as 1 plus. So its oxidation state is +1. And then it can get a little more interesting when you have something that has a polyatomic ion. And so if we look at the periodic table, we can identify that calcium would like to have a 2 plus ion. So its oxidation state is +2. And then once again, we're going to balance our oxygen, our 2 minus, with our H +1, so that if we actually look at this hydroxide, so we know hydroxide typically has a 1 minus charge. And here, our oxygen will have a 2 minus charge, while hydrogen has a 1 plus charge in order to get to this net -1 for the polyatomic ion. So it depends sort of how we build up these polyatomic ions that we determine oxidation state. But while these are useful examples maybe to look at and to try to reflect on, it's useful to have an actual process for describing how to determine oxidation state. So I've recreated the flow of rules that's present in the book. And if you don't like this depiction of it, you can go and read the version in the book, which sort of isn't laid out in this way, but is laid out in paragraph form. But I want to walk you through how we determine oxidation state using the set of rules that they provide. So the first thing that I did on the previous slide is if I had an atom by itself, then as we've talked about before, it's in its elemental state. And in that elemental state, its charge and its oxidation state is 0. If we are looking at an ion that's one atom by itself, such as calcium on the last slide, its oxidation state is going to be equal to the charge on the ion. So calcium likes to be 2+, so our oxidation state is going to be +2. And then we get to sort of where we have to start to calculate oxidation states or define them based on some more specific rules. And so these rules operate in this order. So the first thing you do is if you have a hydrogen, it's going to be +1 if it's bound with nonmetals and -1 if it's bound with metals. Next, fluorine is always -1, such that if you have oxygen, while it typically prefers to be in -2, it could be in -1 with a peroxide, which is to say that you have something that's O2 that needs to have a charge of 2-. Or if it's bound with hydrogen, it could also potentially be where you have something that has 2 oxygens but needs to be a -1, which we call a superoxide. And so we get these by interacting with hydrogen, which the rule is that this oxidation state is set first before we set the oxidation state of oxygen. And then if oxygen is bound with fluorine, it can potentially be forced to be positive because fluorine will always have a -1. And then if you get to the rest of the halogens, then you're going to have a -1 unless you're interacting with oxygen or some other rule that precedes this. And then to determine any remaining oxidation states, what you can use is that the sum of those oxidation numbers must equal the charge on the molecule or the polyatomic ion. So in the last slide, when I talked about something like OH-, I pointed out that oxygen will have 2-, hydrogen will have 1+, and these two will sum up to be 1-. And so if we're talking about oxidation states here, the oxidation state of this OH as a whole is going to need to add to -1. And so this can help us for species where we don't have a rule. It helps us calculate what those charges are. And I'm going to walk us through an example on the next slide. But this is just a general layout in the rules in a way that I find easier to read than reading the text in the book. So let's talk about an example. So phosphoric acid here is something we can try to determine the oxidation state for. And so our first rule is if it's elemental, then it's 0. And we don't have anything elemental here. And then it says a monatomic ion is equal to that ion's charge. And so we can here pretend that we can split this into an ionic compound. And we can have 3H+ and PO4 3-. So this can be our sort of first guess. And so then our H+, like we might anticipate, is going to have an oxidation state of 1+. And now we have to look at phosphate. And so phosphate isn't a monoatomic ion. It has more than one type of ion. So we have to look here. And so we don't have a hydrogen. We don't have a fluorine in phosphate, but we do have an oxygen. And so oxygen here is going to have an oxidation state of -2. So now what we have, if we have phosphate, we have -2 per oxygen, which means that we have -2 times 4. We have a total of -8 in oxidation state on oxygen. And we know that we want to get up to 3-. So we want -3 equals -8 plus the oxidation state for phosphorus, which is this sort of last purple step. And what this allows us to see is that in order to get a -3, our X, or our oxidation state for phosphate, has to be +5. So then we can label the oxidation state of phosphorus as +5. So even though we didn't have a rule for how to label phosphorus, we're able to use the charges that we've been talking about in this course to calculate that oxidation state using what we know about oxygen's oxidation state. So now I want to give you the opportunity to do some practice yourself. And so I recommend pausing the video and trying to calculate the oxidation state of the different elements in these compounds. And then on the next slide, I'm going to show my work for how I would calculate the results here. And I'll walk through a few of them, and the rest of them you can reflect on. So pause the video now, and we'll try to talk through this in just a second. So I did the calculation for each row here. And what I did is first, for calcium carbonate, for example, I split it into calcium and carbonate. And calcium is going to be +2 based on the charge that its ion likes to be. And oxygen is the first thing I'll specify as -2. So if I have -2 times 3, I get -6 as my oxidation state here. When I need it to sum to a total of 2- to match the charge on carbonate, which means that carbon has an oxidation state of +4. If we look down at O2F2, it's a little interesting because our fluorine is the first thing that we assign, and it has an oxidation state of -1. And since we have 2 fluorines with -1 for each of them, and we need to have a net charge of 0 with 2 oxygens, we actually have to set oxygen as +1 in order to balance out this compound. And so these are just some samples you can walk through of how we use this set of rules to determine oxidation state. And it's something we'll practice more on the worksheet in class.